I want to start a diet and lose some weight. This is a very common sentence that we hear all the time. But have you ever wondered how your weight would change on another planet? For example, did you know that your weight on the moon would be only 1/6 of your weight on the Earth? And what about other planets? Watch this video and I'll tell you. Before discovering how your weight would change on other planets, we have to talk about a very important concept in physics: the difference between mass and weight. In fact, in normal life, we often use these two terms as they were the same thing. However, this is not correct. When we say my weight is 70 kilograms, we're making a mistake, at least from a scientific point of view. In fact, 70 kilograms refers to our mass, not our weight. What is the difference between the two then? Let's start by talking about mass. In simple words, mass is a quantity describing the amount of matter in a body. So when we say, for instance, that a child has a mass of 20 kilograms and a dog has a mass of 5 kilograms, we are just saying that the child contains a greater amount of matter than the dog. One thing that should be clear is that mass of a body is an intrinsic property of the body itself. So it doesn't change if we change its location. This means that it doesn't matter if we are on Earth or on the Moon or on Mars. The mass of the child will always be 20 kilograms, and the mass of the dog will always be 5 kilograms. That's because the amount of matter inside each of the two bodies does not change. What about weight instead? Weight instead is the direct effect of the force of gravity on a body. We all know that on Earth, the force of gravity acts on all objects, attracting them towards the ground. The strength of this force, however, depends on the mass of the object. In fact, the larger the mass of a body, the stronger the force of gravity acting on it. To be more precise, the strength of the gravitational force on an object on Earth is given by this simple formula: F equals m times g. And this F indeed is what we call weight. Here, m is the mass of the body, so you can see that when the mass is larger, the weight is larger as well. But what about g? G is a special constant known as the acceleration of gravity. In simple words, this particular constant tells us how strong is gravity at a certain location. For example, on the surface of the Earth, the value of G is approximately 9.8. In reality, this value is not exactly the same in all places in the world, since it slightly changes. However, we can neglect these small differences for the purpose of our discussion. Okay, so to get the weight of a body on the Earth, we just have to multiply its mass by this magic number G. At this point, there should be a question in your mind. When you stand on a scale, the measurement is measuring how strong is your body, pressing on the plate of the scale. But this depends on the force of gravity. So the scale must be measuring your weight, not your mass, right? The answer is yes. However, why do we see a mass, for example 70 kilograms, on the display then? The reason is the scale first measures your weight, but then it converts it into a mass. This can be done easily by looking again at our simple formula: F equals m times g. In fact, the scale knows the value of g, which is 9.8 on the Earth, as we said. So it is perfectly capable of calculating the value of our mass, m, once it has measured our weight, f. Okay, so after this short introduction about mass and weight, we are now able to broaden our view and see what happens if we travel to space and to other planets. Let's imagine that an astronaut of 70 kilograms now jumps on a rocket and starts a journey to space. What happens to his weight? First of all, let's remind that his mass will never change during the journey. This is because the amount of matter that he has in his body is always the same. However, his weight, which remember is a measure of how strong gravity is acting on him, changes. This is because the value of g, the acceleration of gravity, changes as he moves farther away from the Earth. In particular, g decreases as he moves away from the Earth's surface because he is moving away from the source of gravity, the Earth in this case, that attracts him towards the ground. When the spaceship will be sufficiently away from the Earth to not feel any more its gravitational attraction, the value of g will become 0. This means that the astronaut's weight will be 0 as well. We call this weightless condition. In this situation, he would be able to float freely inside the spaceship because there is no force of gravity attracting him towards the floor. But what happens when he reaches, let's say, the moon? Stick with me and I'll tell you in a few moments. Before we continue our journey to see how gravity changes outside the Earth, be sure to like or dislike the video so that we can continue to improve and make these videos better for you, the viewer. Plus, be sure to subscribe to the channel, clicking the bell so that you don't miss any of our weekly videos. So the astronaut is now in his spaceship, traveling towards the moon. He is now weightless, but when he approaches the moon, there will be a new source of gravitational attraction, the moon itself. However, the moon is much smaller than the Earth, so it exerts a weaker force of gravity. To be more precise, the reason gravity is lower on the moon is that the mass of the moon is much lower than that of the Earth. The difference in the force of gravity is reflected into the value of g. On the moon, its value is only 1.6, compared to the Earth where it was 9.8. It's about a factor of 6 lower. This means that gravity on the moon is 6 times weaker than that on Earth. And if you remember our formula, F equals m times g, you will immediately realize that the weight of the astronaut on the moon will also be 6 times lower than that on Earth. So if his mass is 70 kilograms, his weight on the Earth would be 70 times 9.8, which equals to 686 newtons. The newton is the unit of measurement used for the weight in honor of the famous scientist who first described gravity. Instead, his weight on the moon would be 70 times 1.6, which equals 112 newtons. A very large difference. This difference is so wide that if he jumps on the moon, he would be able to reach the roof of a house. Okay, this is for the moon, but what about the other planets of the solar system? Let's move to Jupiter, the biggest of the planets. This is also the planet having the strongest gravity in the whole solar system. In fact, the value of g, the acceleration of gravity, on Jupiter's surface is 24.8. It's about 2.5 times larger than the value of g on Earth. Thus, if we take again our astronaut of 70 kilograms traveling through space, if he reached Jupiter, his weight would be 70 times 24.8, which would equal to 1,736 newtons. In fact, gravity is so strong on Jupiter that he would feel crushed to the ground, and it would be very hard for him to walk on the surface, let alone to jump. In reality, Jupiter has no surface, being made up of gases only, but that's another story. What about other planets? Venus, which is the planet most similar to the Earth in the solar system, has a value of 8.9 for the acceleration of gravity, which is quite similar to the Earth, 9.8. This means that the astronaut's weight on Venus will be just slightly lower than his weight on the Earth, while Mars, the red planet, has a value of 3.7 for the acceleration of gravity, which is much lower than the Earth. In fact, the astronaut's weight on Mars would be less than half than that on Earth. And what about the Sun? Well, the Sun is the most massive object in our solar system. This means that it is the object exerting the largest force of gravity. In fact, if we could reach the Sun's surface without burning, an impossible mission, we would feel an acceleration of gravity of 274. This is about 28 times stronger than the gravity on the Earth. So on the Sun's surface, the astronaut would weigh 28 times more than on the Earth. Here, the weight of our hypothetical astronaut would be 70 times 274, which is equal to 19,180 newtons. We can even continue our journey and go outside the solar system. How does gravity act on other objects? In fact, there are distant objects which are even more massive than our Sun, which is just a middle-sized star, much smaller than others. So where in the universe would the weight of the astronaut be the greatest? To find the answer, we have to look at those objects exerting the strongest gravity: neutron stars and black holes. Neutron stars are formed after the explosion of massive stars. This event is called a supernova. Their composition is very different from normal stars, since they are composed almost entirely of neutrons. These stars are characterized by an extremely high density. As a consequence, gravity on their surface is very strong. In fact, the value of g, the acceleration of gravity, is in the order of 10 to the power of 12. This is a very huge number. Remember, on the Sun this value was only 274, so hypothetically the weight of our astronaut on the surface of a neutron star would be something like trillions of newtons. The force of gravity would be so strong that he would be smashed on the surface instantaneously. However, this is not the end yet. Our astronaut can even experience some more extreme conditions if he would travel to a black hole. Black holes are also produced after a supernova event. but only when the mass of the original star is above a certain threshold. Black holes are mysterious objects. Their density is the highest in the universe, and their gravity is so strong that even light cannot escape from it, and it is captured by the black hole. As our indestructible astronaut approaches the black hole, he would feel a stronger and stronger force of gravity, and he would undergo a very bizarre phenomenon called spaghettification. What is it? The part of the body of the astronaut closer to the black hole feels a much stronger gravity than the part farther away, and because of this, he will be stretched into a long, thin shape, like spaghetti. This effect is so strong that nothing can withstand it. Even stars close to a black hole have been observed to undergo this phenomenon. So stay away from a black hole if you don't want to look like a noodle. So what is the weight of the astronaut in the proximity of the black hole? Well, at this point it probably doesn't even make sense to try to quantify it. It must be in the order of trillions of newtons. Our astronaut is probably long gone now. In the end, we must feel very lucky to live on Earth. In fact, the conditions of gravity on our planet are just right. If gravity was too strong or too weak, life would have probably never occurred on Earth. That's all for this video. Thanks for watching, everyone. Are you amazed by how gravity can change the weight of a body outside of Earth? Do you want to know something more about gravity and weight? Let us know in the comments below. Be sure to subscribe, and I'll see you next time on the channel.